Swayam Prabha. Digital India. Educated India.
Welcome friends to this second lecture of week 7 of this online NPTEL online certification course of environmental soil chemistry, and in this week we are talking about redox chemistry of soils. So, in the first lecture we have briefly talked about different concepts of what is redox potential and what is the relationship between the redox potential as well as the pH and PE. So, before going to the new topic in this week, in this lecture, I want to give you a quick recap of whatever we have discussed, so that it will be easy for you guys to relate the new things. So, in the previous lecture, we started, these are the concepts which we are going to discuss in this week: oxidation reduction reactions and oxidation reduction potentials or redox potential, then EH versus pH and PE versus pH relationship, and measurement and use of redox potential, submerged soils, and redox reactions involving inorganic and organic pollutants. So, in the first lecture we have talked about the difference between the oxidation reduction. You all know that oxidation means the loss of electrons in the transfer process, whereas reduction means there is a gain of electrons. And in case of oxidation, oxidized components or oxidant is the electron acceptor, whereas in case of reduction, the reduced component or reductant is the electron donor, and the oxidant must be in close contact with the reductant in soil solution. As we have seen in this picture, the reducing agent and oxidizing agent has to be they have to be in close proximity to be oxidized and reduced. Now, regarding the redox potential, we can in short we can denote this as EH, and redox potential expresses the tendency of environment to receive or supply the electrons, and we have discussed the redox potential on the light of these iron oxygen reactions to produce the ferric oxides. Remember that an oxic environment has a high redox potential because oxygen is available as an electron acceptor. In contrast, an anoxic environment has low redox potential because of the absence of oxygen. And then I showed you the selected reduction half reaction, which are very important for soil, natural water, plant and microbial system. We have seen the nitrogenous species, we have seen oxygen species, we have seen sulfur species, iron manganese compound, their logarithmic of equilibrium constant as well as their PE value at two different pH, pH 5 and pH 7. And so we have seen these half reactions for carbon species, pollutant and nutrient groups as well as analytical couples also. Then we have seen the redox reaction, the generalized form of the redox reaction in the soil, and then based on that we have they illustrated the redox reaction of FeOH whole 3 according to Patrick et al. And then we have seen how these FeOH whole 3 first reduced to ferrous, and then how this organic matter acts as a reducing agent. Then we have discussed this reduction in terms of Nernst equation. This is the Nernst equation which can be employed to express the reaction in terms of electrochemical energy or millivolt, and this is the Nernst equation. We have expressed this Nernst equation where the the Gibbs free energy is basically minus NFE. So, we have discussed all these things or standard free energy. So, we have expressed this redox reaction or redox potential or in terms of this Nernst equation. So, it is the and also the standard half cell reduction reaction. Remember that the oxidation potential are more often used in chemistry, whereas in soil we more generally use the reduction potential. Remember the Nernst equation is valid for predicting the activity of the oxidized and reduced species only in case of a system which is in equilibrium. However, in soil we seldom see the equilibrium between different reaction. So, then we have discussed about the EH and pH relationship using the values of the molar gas constant as well as Faraday constant, and then absolute temperature in Kelvin. And so, we have expressed the EH and pH relationship, which is basically we can express that EH MV equal to basically E0 minus 59 minus by n log reduced over oxidized minus 59 m by n pH. And basically when the m and n basically shows the protons and electrons, when this m by n ratio become 1, then we can say that the EH would change by 59 millivolt per every unit change in pH. So, we can simplify this relationship between EH and pH relationship. So, also we have discussed the implication of EH and pH relationship. Remember that when EH is positive and high, then it is basically showing the strongly oxidizing system, whereas in case of when the EH is negative and low, that basically shows the strongly reducing systems. And then we have talked about the more about the EH pH relationship. Remember, EH just like a pH is an intensity factor, and the oxide nitrogen range has been defined EH values from plus 250 millivolt to 100 millivolt, and the iron basically the redox potential of iron or the major reaction of conversion of iron basically ranges between 100 to 0 millivolt, and the sulphate ranges from 0 to minus 20 to 100 millivolt, whereas the methane hydrogen ranges between methane hydrogen range with a value of less than 200 millivolt. And then we have divide the we have discussed the EH and pH graph, and then we divide the zone, as you can see here, into 3 zones. That is, one is the oxidized and normal zone, and then seasonally saturated or wet zone, and waterlogged zone or anoxic zone. So, based on that we can calculate, we can see the relationship between the EH and pH. Now, today we are going to discuss from this slide. So, basically EH and pH relationship, you can see the reduction half potential, this reduction half reaction which is given in our previous equation 1 can also be expressed in terms of an equilibrium constant K0 value. So, K0 basically is basically can be expressed by reduced species, concentration of reduced species by concentration of oxidized species, and electron to the power n and proton to the power m. So, expressed we can, if we can take the logarithmic form from this equation 8, let us consider this an equation 8. So, if you convert it to the logarithmic form, then we will get the log of K0, then log of reduced species concentration, log of oxidized species concentration, minus n log of electron concentration, and m log of H plus n concentration. Now, here this negative logarithm of electron concentration term in this equation is known as the PE, and it is just like the similar way as pH is basically the negative logarithm of proton concentration or hydrogen ion concentration. Remember that the PE is an intensity factor, as it is an index of electron free energy level per mole of electron. Just like pH and EH, the PE is also an intensity factor because it shows the negative logarithm of electron concentration. So, again the PE and PE sometime we can express in terms of P capital E. So, basically the concept is it is basically used instead of redox potential. So, this PE and EH can be used interchangeably to denote the oxidation reduction state of a system. So, PE is used instead of redox potential sometime to characterize the submerged soil. Now, submerged soil is a very important phenomena in case of soil in case of soil oxidation reduction chemistry. Now, this reduction potential is more applicable for different transformation which are happening in the submerged soils. So, in the submerged soil instead of EH we sometimes use the PE concept also. Now, we know that PE is basically negative logarithm of electron concentration we can and PE is basically equal to EH by 0.0591. Now, P is a negative logarithm of electron activity, we know that. Now, P is large and positive in strongly oxidizing system, just like in case of in case of EH it is basically positive in case of oxidizing system, strongly oxidizing system. However, P is also low and negative in strongly reducing system, just like as EH. So, the implication of PE and EH are basically same. Generally, we use the term PE in terms of defining when we are trying to define the chemical dynamics in submerged soil. So, what is submerged soil? We will see in a moment. Now, what are the other implications of PE in soils? Now, in strongly oxidizing system, the electron activity is low and PE is large and positive. I have already told you, just like as the EH. In terms of EH, in the oxidized system and aerobic soil, you will see that it is positive in terms of millivolts in it. So, similarly in case of strongly oxidizing system also electron activity is low and that is why the PE is large and positive. Now, in reducing system PE is small and negative. So, the scientist Posito in 1989 he proposed that some range of PE which we can see generally in oxic soil, suboxic soil and anoxic soils. Now, in the oxic soil we can see a PE value of greater than 7, whereas in case of suboxic soil PE basically ranges between +2 to +7. However, in case of anoxic soil the PE generally is less than +2 all at pH 7. So, these ranges are consistent with redox control by oxygen, nitrogen, manganese iron and sulfur couples. So, basically these oxygen, nitrogen, manganese iron, sulfur couples are very important reactions as far as the redox reactions in the submerged soil is concerned. So, these ranges they can be these ranges are true when you compare these oxygen, nitrogen, manganese iron and sulfur couples in the submerged soils. And the PE range for most of the soil very generally it varies from -6 to +12. So, this is basically the implication of the PE. Again PE is basically negative logarithm of electron concentration and in case of oxic soil, strongly oxidized soil, the value of electron activity is low. As a result, the PE is large and positive, vice versa in case of anoxic soil. Now, that is why in case of in defining the redox reaction in submerged soils or anoxic soil, we generally use PE sometime instead of EH. It varies from -6 to +12. However, in oxic soil it is the range is greater than 7. In case of suboxic soil or periodically saturated soil, it varies from +2 to +7. However, in case of anoxic soil, it is less than +2. So, if we just rearrange the equation 9. So, what was the equation 9? So, if you go back and see, this is the equation 9 we have talked about, log k equal to logarithmic of reduced reduced species concentration minus logarithm of oxidized species concentration minus n log e to the electron minus m log h plus. So, basically if we take this equation and if we rearrange this equation, we can arrive at an expression that relates PE to pH. So, you can see here, if we rearrange that, then it becomes P equal to minus log K0 minus logarithm of reduce species concentration plus logarithmic of oxidized species concentration by N minus M by N pH. Now, which represent a straight line with a slope of M slash N. So, if we relate the PE to pH in a graph, we will see that there is a straight line where the slope is M by N, we can see here just like here, an intercept given in this bracket. So, this bracketed portion is basically the intercept. Now, this intercept, as you can see from this formula, is a function of log of equilibrium constant or K0 for the half reaction and the activities of the oxidized and the reduced species. Now, for calculating this log K0, we have already calculated this log K0 in our previous modules. So, you can see that the intercept, which is basically a combination of these terms, it basically depends on log K0 for the half reaction and also the activities of the oxidized and reduced species, as you can see in the bracket, in the parenthesis, concentration of reduced species as well as concentration of oxidized species. So, when there is only one electron transfer, that means when there n equal to 1 and the consumption of one proton, that is m equal to also 1, and when the concentration of the reduced species is equal to the concentration of the oxidized species. So, basically these and these are same, concentration of oxidized species, concentration of reduced species, n equal to 1. So, basically these two nullify each other, and then m minus n is also 1, because we are considering that m equal to 1 and n equal to 1, that is 1 proton, consumption of 1 proton and 1 electron transfer. Then these equation can be simplified equal to Pe, and this pH will come to this side. So, Pe plus pH equal to log K0. Okay. Now, at pH 0, when the pH is 0, so obviously P equal to log K0. So, basically this is the general relationship between this negative logarithm of hydrogen ion concentration and negative logarithm of electron concentration as well as log of equilibrium constant. So, this can be simplified for pH 0 when P equal to logarithm of K 0. So, when the pH nullifies, the pH becomes 0, then we can see here P equals to logarithm of equilibrium and equilibrium concentration. Now, the P in soils also one can relate this logarithmic of equilibrium constant to this delta Gr also using this equation, just like this delta Gr is equal to minus RT ln K0. Now, at 298 Kelvin and converting it to logarithmic, then we can see when we are converting these natural logarithms to log, then we can get this 5.71, and then from there we can have this relationship. Now, this 5.71 derived from the product of RT into 2.303. We know that when we convert this natural logarithm to log, then we have to use this factor 2.303, and RT, you know, R is basically molar gas constant and T is the temperature in Kelvin. So, when you multiply all these things, then we can get a value of 5.71. So, basically we simplify this in terms of this free energy, Gibbs free energy with the log of equilibrium constant. So, therefore, this logarithmic of K0 or log of equilibrium constant could be estimated by knowing the free energies formation, that is delta 0 F of water and the reduced and oxidized species, since those for H plus and electron are 0 by convention. So, we can see that we can simplify the whole reaction in terms of these free energies of formation as well as the logarithm of the equilibrium constant. So, we can see here these values are basically what we are We have seen this table previously. So, this is the half reaction of reduction for different species starting from nitrogen species, oxygen species, sulfur species, iron and manganese compounds. So, some of the observation which we can see from here, the values of logarithm of K0 can be used to predict whether a reduction and oxidation reaction will combine to affect the transfer of electron from reductant to oxidant. So, by seeing these values we can conclude whether a reduction and oxidation reaction will occur, and if the reduction and oxidation will occur, whether how the electron transfer will how this electron will transfer from the reductant to oxidant. So, you can see here the log K0 values here are given in descending order. So, we can get the highest log K0 value here, and then we are getting it in descending order, and our pH values at pH equal to 0. So, when the activities of oxidant and reductant are basically 1 and as standard, so it is reductant. So, oxidant and reductant are 1 and the standard difference pE values for the reaction. So, we can see standard difference pH values for two different pH, one is pH 7 and one other is pH 5. So, we can see for each of these species, nitrogen species, oxygen species, sulfur species and iron inorganic compound, all these reactions are arranged in terms of basically descending order of their log of equilibrium constant. Now, remember one thing, one thumb rule, that the larger the value of this K0 or P. So, similarly you can see here one more thing, here not only the ascending order of the K0 logarithm of K0, but you can see I am sorry that the descending order of log of K0, and also you can see descending order of log of PE also in both these cases more or less. So, the larger the value of K0 or PE, greater the tendency of an oxidant to be reduced. Obviously, higher PE basically indicates higher P basically indicates oxidized system. So, a species which is highly oxidized will be will have more tendency to be reduced. So, it is quite natural that a species which has a higher PE value, such as in case of oxidized system, as well as it has high logarithm of K0 value, then that species will be more will have more tendency to get reduced. So, therefore, an oxidant is a given reaction, reduction half reaction can oxidize the reductant in another half reaction with a lower P at a particular pH. So, obviously, you can see here one example that this N2O, that is the nitrous oxide. Nitrous oxide, when it is reacting with one electron, that means it is getting reduced. So, we are here getting after reduction of this nitrous oxide, we are getting elemental nitrogen. This elemental nitrogen is more amenable to reduce than the other nitrogenous compound which are presented below. So, these nitrogen will further reduced into other species. So, this is how this reaction basically goes on. So, this basically denotes in terms of this logarithm of K0 values as well as PE values. So, let us see some other examples also. Now, PE and pH stability lines between the oxidized and reduced species, for we can see here this is basically a PE, we are plotting pH and PE here in a x and y axis, and basically it shows the PE and pH stability lines. These lines are basically showing PE and pH stability lines between the oxidized and reduced species for several redox couples. So, we can see here for example, Mn3 plus, Mn4 plus and Mn2 plus. Similarly, we can see here Fe3 plus, Fe2 plus, Cu2 plus, Cu plus. So, we can see differ several redox couples, and these lines are showing the stability between the oxidized and the reduced species for these different redox couples. So, the line for Fe you can see here, this is the line for Fe. Okay. So, this is basically this dotted line is for the AC, which I am drawing right now. So, the line for AC is often considered as the dividing point between the aerobic, which is oxidized, and an aerobic, which is basically reduced soil. Okay. So, in anaerobic soil, basically whatever is above this line is considered is in the oxic condition or oxidized condition, aerobic soil condition, and whatever species which are present below this line are considered in the anoxic condition or in case of reduced condition. Now, in aerobic soil, oxidized species stay oxidized even though thermodynamic tendency is towards reduction. So, obviously, although the oxidized species tends to reduce themselves easily, but in the aerobic soil, oxidized species try to stay oxidized, okay, as indicated by their high Pe values. Below this iron line, so whatever species are there below this iron line, these reduced species are prevalent even though the thermodynamic tendency is towards oxidation. So, obviously, just opposite to the oxidized species, in when the below the iron line, when the reduced species are there, the reduced species will be also have more tendency to get oxidized. However, they tend to be in the reduced condition as compared to the oxidized condition. So, you can see this is basically a kind of a border line above which the oxidized species try to stay as an oxidized form, and the species which are below this line try to stay in the reduced form. So, basically this is showing the stability lines between the oxidized and reduced species for several redox couples. Obviously, solid phases of manganese, iron are at unit activity, and the activities of other species are designated if not equal within a couple. So, you can see here different couples are there, different redox couples are there for manganese, for nitrogen, you can see for chromium and so on so forth, from iron, and then from sulfur you can see different redox couples are there depending on different conditions. So, these basically shows their stability. So, if we move ahead, we will also see one important thing, that this sulphide here, this is sulphide. So, this sulphide and sulphate, so this is oxidized and redox. So, basically this is a redox couple. So, this is the line, stability line. So, we can see that sulphide is easily oxidized and nitrate is easily reduced, because this sulphide or sulphate, this couple remain below this cutoff line or the border line, that is Fe3, Fe2 border line. So, basically here the sulphide is easily oxidized as compared to the nitrite. You see here the nitrite, which is obviously easily reduced to other nitrogenous form like nitrogen. So, this is how we can define the state of oxidation and reduction of different redox couples based on their pH and Pe relationship. So, also we can see here this is a Pe and pH diagram for manganese. We are plotting the pH in the x axis and plotting the P in the y axis, and these are line for different species of different other species, like this for chromium, selenium, arsenic and vanadium, plutonium. Now, we can see that the manganese oxide can oxidize Pu3 to Pu5, as you can see Pu3 to Pu5 it can oxidized, and also vanadium 3 to vanadium 5 it can oxidized. There is AS3 to AS5, that is arsenite to arsenate, it can oxidize. Then selenium 4 to selenium 6, it can oxidize, and also it can oxidize from chromium 3 to chromium 6. We will see this in more details in our next lectures, how these different conversion happens. So, you can see that these different. So, because a different PE versus pH relation, we can see that the conversion of different oxidized form of this plutonium, vanadium, and then arsenic, selenium, and chromium mediated by manganese oxides. Now, because the P for each of these couples is below the P of manganese oxide. So, it is very clear these the P values of these each couples, that is chromium 3, chromium 6, selenium 4, selenium 6, arsenite, arsenate, and then vanadium 5, vanadium 3, all their P values are basically below the P values of manganese. So, as a result of that, manganese has more tendency to get reduced, and when it is reducing, simultaneously it is oxidizing this species. So, that justify why manganese oxide can oxidize these species from one oxidation state to another oxidation state. So, guys, I hope that you have learned something new in this lecture. Let us wrap up this lecture here, and we will start from here in the next lecture, that is third lecture of week 7, and then we will see in details about submerged soils and other aquatic soils. Thank you very much.